Okay. Maybe your pointer. Yep, I think I'm good to go. Okay. Here we go. We will try to stay on time, but of course, I don't want to limit any questions and so on. But as you can see, if you ask questions during the talk, it's the best because we're always running out of time. One more very, very important point. Not only are there bathrooms on the top level here, but there's bathrooms on the bottom in case you know the single occupancy bathrooms up here are occupied. Okay, so we have one more talk before lunchtime, which is here. Bruce Gaulin, McMaster University. Thank you for coming, Bruce. Who I learned had never come here since
a postdoc interview.
Since I started grad school. I don't earlier than that. So thank you, Bruce.
Yeah, no, my pleasure. Yeah, no, it's a wonderful event, and I'm.
Turn your mic on.
Sorry. Is that better? Is that better now?
There we go.
Okay. Yeah, so it's a wonderful event, and I'm very pleased to be here. And like Raphael, please stop and ask questions at any point. So I'm from McMaster University here, and we have an institute that's not unlike the institute here, the Brockles Institute, and I belong to an international organization that's based in Canada. That's called CFAR, the Canadian Institute for Advanced Research, which actually JP is also a member of. And just a slight modification of what JP was saying about the first instance of usage of quantum materials in the community. The one that I'm familiar with is that our program is called the Quantum Materials Program. And I believe that was first named in 2005. So it goes actually way back. And the person who was credited with first naming it was an optical spectroscopist, pretty well known, named Tom Timmis, my colleague at McMaster. And sadly, he passed away last he was 90 some odd years old and a very successful career and life, a very happy life. Anyway, it's a little bit sad, but it's not that sad. Right. So what I do is actually mostly neutron scattering and materials prep and crystal growth. And you know, given the nature of the activities here at Maryland and the practicals that you're going to do, and the fact that there's another at least 3 neutron scatterers that we're going to talk later on, I thought I should probably focus on the materials synthesis and crystal growth effort that we have, and just try to give you some survey and some background into that. And actually, the materials I'm going to focus on are materials that are relevant to study of highly frustrated magnetism. And this is mostly in magnetic insulators, but it can also be in, there are versions of these materials that are metals, many of them, and even superconductors. So I'm also going to be talking about insulators. And highly frustrated magnets are magnets that have exotic, typically disordered ground states, or at least we would, when we're talking about them in an idealized way, we're imagining that they have some sort of idealized liquid-like ground state. The most topical version of these are quantum state liquids. And most of the candidate materials that are of interest are based on a few crystallographic architectural paradigms. And as I'll discuss, there are paradigms that are based on triangles and tetrahedra. So those are the building blocks that we start with, and then we build up 3-dimensional crystals and go from there. So if I'm going to talk about,
Just click on the screen.
Oh, there we go.
Let's see if it works.
Yeah, it does. Yeah, so if I'm going to talk about exotic ground states and disordered ground states, of course, that isn't what happens in most magnetic insulators and most magnetic materials. I mean, what normally happens is that a material will have a phase transition at some temperature, and that phase transition will take material from some entropy dominated high temperature state to some energy dominated low temperature state, and the low temperature state will be ordered. Okay? And actually, this is very well understood. So this is what's discussed in your textbooks, Ashcroft and Merman and whatnot. And so we imagine that we've got some arrangement of magnetic dipole moments on a non-frustrated lattice. So this is a bipartite lattice, a lattice that can be decomposed into two interpenetrating pieces. And so we have a square lattice in this case. And we've got these little dipole moments, which we imagine as classical little arrows. And these magnetic moments will interact with each other via some relatively simple Hamiltonian. And this Hamiltonian is known as the Heisenberg Hamiltonian, but there's many variations on the theme. And so we normally think of the interactions being strongest or maybe only being relevant at the near neighbor level. And so the system can lower its energy by either having near neighbors be parallel to each other, in which case J is negative, or anti-parallel to each other, in which case J is positive. And these, of course, are ferromagnetism and anti-ferromagnetism. And so long as we have this sort of bipartite unfrustrated lattice, then from a statistical mechanics point of view, these problems are exactly the same. But I'm just going to show you the solution to this sort of problem. So this is a classical Monte Carlo simulation of a two-dimensional Eisenhower. And each of the little squares is a spin, and the spin can either be up, in which case it's a black square, or down, in which case it's a white square. And you can see that if you're at high temperatures, this is the entropy dominated regime, there's as much black as white. And it's not that there are no correlations, but there are no very long range correlations. Okay. And whereas if you go down to low temperatures, then you can see that there's more, if this is a ferromagnet, there's more black spins, so there's more up spins than down spins. And in fact, you've got little islands of down spins in a sea of up spins. But what you can see immediately, even just at a glance, is that the symmetry has been broken as you go to low temperatures. There was nothing in the Hamiltonian or any other phrasing of the problem that told you that the upspin should win, yet the upspin is won. Okay? And if you were to redo the simulations, with a 50% probability, the downspin would be, well, one of them would. Okay? And that's a symmetry breaking. Okay? And this is exactly what we are not interested in studying. So materials that end up having a phase transition that is at some elevated temperature that's roughly consistent with the strength of the interaction that's present, that's what conventionally happens. And we're looking for those materials which don't do that. And the reason that they don't do that, or the reason in the materials that we're studying that they don't do that, is because the nature of the interactions, and the geometry of the local unit on which the spins are arranged end up competing against each other. So this is a case that's been known for a long time. It's where our fundamental building block is a triangle, and we've got little dipole moments, again classical, so we think of them as little vectors. And we've decorated our building block, our triangle, with these spins, and they're antiferromagnetically coupled. But obviously, there's no way you can have three pairs of antiferromagnetically coupled spins on a triangle. One of the sides or one of the bonds on the triangle has to be frustrated. And so there's a degeneracy of three associated with each triangle. Okay, and then when you put the triangles together to fill, in this case, two-dimensional space. Okay, so there's two easy ways you can do this. You can have tiling of two-dimensional plane, which is an edge sharing, tiling of edge sharing triangles, and that gives you the familiar triangular lattice, very common in nature, appears as the basal plane of all hexagonal crystals, for example. Or this less common, but still not uncommon lattice, which is a network of corner sharing triangles, and that's referred to as the Kagame lattice. Okay, and in both cases, you start off with the degeneracy of 3 for each triangle, and then as you make the system bigger and bigger and bigger, you grow the degeneracy. And at least in the case of the Kagame system, that growth of the degeneracy as you make the number of triangles involved in the 2-dimensional net bigger and bigger and bigger, that's enough to preclude the occurrence of conventional phase transition. And so that will give you some disordered state, or can give you some disordered state at low temperatures. Okay. And actually, what's kind of interesting, I mean, I'm just going to do a very brief historical survey, is that this field of geometrically frustrated magnetism, it's essentially as old as the field of antiferromagnetism itself. And so actually, the real understanding of antiferromagnetism had to wait until the development of neutron diffraction techniques. Actually, there was some understanding of antiferromagnetism before then, based on Louis Néel's work and magnetization measurements. But really understanding, antiferromagnetic structures and such required the invention of nuclear reactors, which was a consequence of the Manhattan Project. And actually, this was the discovery paper of antiferromagnetism being measured and studied by neutron diffraction techniques by Shaw and Smart. But you can see it's 1949, right after the end of the Second World War. And our theory colleagues, was Raphael around, or just going to try to give him some credit? Okay, our theory colleagues, very fast off the mark, right? So antiferromagnetism had just been discovered, and our theory colleagues were immediately hard at work trying to find a way to screw it up. And so there's this landmark paper by Vanier at Bell Labs at the time, who studied the classical antiferromagnetic Ising model, not on a square lattice like I showed you a moment ago, but on a triangular lattice. And he discovered that in the presence of antiferromagnetic interactions, it didn't have a phase transition down to the lowest temperatures. And there's a whole host of papers. This is another landmark paper from 1973. And I'm not sure if this is completely accurate, but I'm going to credit this with being the first treatment of frustrated antiferromagnetism, but treated quantum mechanically. Okay. And so this was a paper by Phil Anderson, 1973. He published it in this rather obscure bulletin. So he himself, of course, is very famous, and was even very famous then. But this was published in the Materials Research Bulletin, which I think still exists. But it's never been really first choice for a place to publish your very exciting results. And so even though this was a landmark paper, he was introducing the resonating valence bond model, it didn't actually get very much attention. So this was the model that he proposed, was that he imagined that we had 6.5 degrees of freedom that were antiferromagnetically coupled and that were on actually a triangular lattice. However, he, if they're antiferromagnetically coupled, he didn't imagine some sort of an antiferromagnetic Néel state that you would come up with classically. Instead, he imagined the state, it's basically a tiling of the triangular lattice on the basis of singlets, of non-magnetic singlets. So each of these little ellipses is not, an upspin at one side and a downspin at the other, but it's both an upspin and a downspin at each of the sides, and it's the antisymmetric combination of the two. And, he understood at the time that you could make that tiling in a way that formed an ordered state, and this is called a valence bond solid. It breaks translational symmetry. But you could also do it in a way that didn't break translational symmetry and left you with a liquid of these singlets. And in fact, you would add together coherently, all possible tilings. This was if you restricted yourself to 6.5 magnetic moments, which interacted at the near neighbor level, but you didn't have to do that. And so if you had this sort of tiling of singlets, these long singlets would be, just barely held together. So this would give you a gapless quantum spin liquid, and these would give you gapped quantum spin liquids. Okay. But nonetheless, brilliant idea. First time it's been, made known to the public, and virtually nobody was aware of it because of where it was published. But he decided to republish it in a somewhat different format, in a much better venue for getting attention, Science magazine, just at the onset of the discovery of the high temperature superconducting cuprates. And so for that, he of course had to change the lattice from a triangular lattice to a square lattice, to a two-dimensional square lattice. And so he was proposing quantum magnetism in the form of spin-and-a-half degrees of freedom on the copper sites, which are in lanthanum. So this is the crystalline magnetic structure of lanthanum and cuprate, which is the parent compound, cuprate-based high temperature superconductivity, and it has this sort of anti-ferromagnetic structure that you can see here. But he was proposing this different quantum disordered ground state on a square lattice, which again involved this linear combination of random filings of these singlets, which would then form a liquid, a quantum mechanical liquid. So these were the first developments connected with quantum versions of highly frustrated magnets. So actually, in nature and in my own research program, we're actually on a regular basis trying to develop new platforms in which to see this sort of phenomenon. And typically the way we're doing this is we're trying to identify materials which have different tilings of triangles in 2 dimensions and tetrahedra in 3 dimensions. Okay. And so for the triangular case, as I mentioned, triangular lattices are very common in nature, and these are two such material systems. Well, one of which we've been involved in, this one over here. This one we haven't been involved in, but it's another very popular family. So this is the crystal structure of this rare earth-based family. There's at least 2 members to it: ytterbium magnesium gallate and erbium magnesium gallate. And the rare earth ions, which are the erbium 3+ and the ytterbium 3+, they form this network of triangular planes, which are then stacked in an ABC type structure along the 3rd dimension. So it's a stacking of triangular lattices, and both ytterbium 3+ and erbium 3+ can have effective spin-and-a-half degrees of freedom that are present here. So these systems have been very well studied, and one of the quirks about this system is that the magnesium and gallium that actually reside between these layers of the rare earth ions, they're actually not that different in ionic size from each other, and they're also not that different in charge from each other. So if the rare earth ion is 3+, then magnesium would be 2+, and gallium would be 3+, and oxygen, of course, is 2-. Okay, the oxygen isn't shown here. But there's not enough difference in this system between the size and the charge of the magnesium and the size and charge of gallium. And the net result is that the magnesium and the gallium are arranged in these hexagonal, or sorry, honeycomb bilayers, but they're not ordered in honeycomb bilayers. So the triangular layers in this material are very well ordered, but the material in between them is not well ordered. So that's in contrast to this family of triangular magnets, and actually, there's quite a few others, where both the triangular layers and the layers in between are both well ordered. So, right. So as I was mentioning, this is the case of triangular lattice. So it's a network of edge sharing triangles. The network of corner sharing triangles is known as the Kagame lattice. And so it's referred to as the Kagame lattice, taking the name from this Japanese, traditional Japanese basket, which is called a Kagame basket. But you can see that it's, you can kind of think of it as a network of interconnected Stars of David, but we would refer to it as a two-dimensional net of corner sharing triangles. And this has actually been a very popular platform for looking for quantum disordered states for the following reason, and that is that if I decorate the vertices of these corner sharing triangles with again, in this case classical spins, and in this case quantum spins over here, and we imagine that the magnetic moments are coupled to each other by again a very simple Hamiltonian, like the Heisenberg Hamiltonian. Okay, and J is positive, then the moments in the pairwise, the moments would like to form, an up-down pair. They'd like the orientation between the spins to be 120 degrees. So if we decorate the Kagame lattice in that way, you discover, of course, that minimizing the energy of this system is done not by having near neighbor spins be anti-parallel to each other, but have them forming this 120-degree structure, sort of a Mercedes-Benz type structure. And you can guess at what the ground state structure would be. Okay, and this is a reasonable guess here. And then you can work out, if the interactions are near neighbor only, what is the classical energy per spin? Okay. And you can see that it's going to depend on what the dot product between spins are, because that's what you get over here. And it's going to depend on the coordination number, how many near neighbors each spin interacts with. And basically that's about it. And the thing about the Kagame lattice is that its coordination number is actually very low. It's 4. Okay. And so if you put in the low coordination number, and you put in the fact that the spins are not anti-parallel to each other, but they make this 120-degree angle, you'll get a certain ground state energy per spin, which is actually minus J over 4. Okay. And if you guess at the ground state for the quantum version of this problem, so you tile the corner sharing triangles with spin 1/2 degrees of freedom that are now arranged in singlets, you get the following ground state energy per spin. And the thing about it, or one of the interesting things about it, is that the coordination number in the quantum problem isn't relevant. Okay, and it isn't relevant because no matter what you do, you're going to tile, every single spin 1/2 with only one other spin 1/2. Right? It doesn't matter what the coordination is, you're going to tie it up with one other neighbor. And so this energy per spin doesn't depend on the coordination, this one does. And the net result is that this gives you a lower ground state energy per spin than this does. And so Kagame antiferromagnets have been very fertile ground for trying to identify quantum disordered systems that are stabilized by geometrical frustration. So both of these systems are actually interesting. The classical system has the interesting property that you would sort of guess that this is an appropriate ground state for it. But actually, the only condition on minimizing the energy here is that every triangle have spins at its vertices that are one of the 3 different colors, right? You don't want any 2 colors the same. And so you can take a line of these spins, like this line here. This line of spins going horizontally is made up of the blue sublattice and the green sublattice, and you can translate it along and have it stop at any position. Okay, so you can take this blue spin, put it here, this green spin, put it here, and that's another ground state that has exactly the same energy. So there's a very large degeneracy associated with exactly how you arrange these 3 sublattices, and so both of these will give you disordered ground states, but this is the lower energy one, and this is the quantum one. Right, and we can also look at the same sort of argument, this energy per spin argument, that's associated with decorating classical spins on a network of corner sharing triangles and a network of edge sharing triangles. And you can see that, in both cases, the ground state that you would guess at is this Mercedes-Benz 120-degree structure. Okay, so it's the same type of structure, but in the triangular case, you've got a coordination number of 6. In the Cagney case, you've got a coordination number of 4. So that means that that argument that I just made for why the quantum Cagney ground state energy per spin is lower than the classical Cagney ground state energy per spin, that would be inverted for the triangular lattice. And the triangular lattice, in the case of the triangular lattice, the coordination number is bigger, so the classical ground state energy per spin is actually the lower of the two. Okay, and this illustrates a more sort of general point in all of these geometrically frustrated lattices that quarter shared architectures tend to be more frustrated, less constrained than edge sharing architectures. So this is probably the best known study of the spin-a-half antiferromagnetic system on the Cagney lattice. It's actually referred to as Herbert-Smithite, and as the name might imply to you, this was originally discovered as a mineral. And this is the chemical composition here, and it's the blue dots that are the copper sites, which carry a spin-a-half magnetic moment, and they're arranged into this Cagney network that you can see here, and then they're stacked on top of each other in the direction perpendicular. And the copper 2+ in the appropriate ligand field environment in this system, these crystal field effects will quench the orbital angular momentum, and it will give you these well-known T2G and EG orbitals that you can doubly occupy with up and down spins. And in the case of copper 2+, you've got 9 d electrons left over, and you've got room for 10 d electrons in these orbitals. So basically, all of the magnetism associated with 8 of the 9 electrons that are here, cancels out, and the only magnetism residing on the copper side is that associated with that last the ninth electron. So that's what is going to be decorating these lattices. And this system has been very well studied. I see Paul and Brooklyn at the very top back there is, this is one of the things that Paul is well known for, is the study of these materials. And I'm just going to point out a couple of things about it. I won't do justice to its study, but I think this was the original paper that was connected with the artificial growth of Herbert-Smithite, so not using an actual mineral that was dug up from some mine, but actually synthesizing it. And actually, it wasn't clear from this paper, but it became clear later on that although the material was quite well ordered, it was not perfectly ordered. And in fact, there are these Cagney layers of copper 3+ that have zinc triangular layers in between, and it is possible to get some of the copper on the zinc site and vice versa. And actually, this type of disorder was noted almost right away. And this is this is a measurement on the green side of this diagram. It's a measurement of just the magnetic susceptibility of the system as a function of temperature, and then the night shift associated with the oxygen 17 NMR measurement. And you can see that they agree well at high temperatures, but then diverge from each other as you get to low temperatures. And that's because the NMR night shift is measuring a local susceptibility, whereas the the squid type measurement that you would do to get the magnetic susceptibility here is the bulk susceptibility, and it's being dominated by free copper spins that would be not in the right position. So actually, you can see this is a very famous paper. Actually, I'm going to make fun of it, but I really shouldn't make fun of it. It's very important paper. But you see, it's got the title "A Structurally Perfect Blah Blah Blah," and I would say, as a rule of thumb, you should never put that in a title because it's always going to come back to bite you. But it also demonstrates that wishful thinking is a big part of what we do. In fact, I think if you didn't have any wishful thinking, you'd sort of be in trouble, right, in your research career. Anyway, an enormous amount of effort has gone into this to try to characterize this sort of disorder. But you can see that this is it's even about 10 years old. These are the first principles estimates of what the exchange interactions would be, and this group of theorists actually considered many possible different interactions. And I don't know how well you can read this, but it's the near neighbor antiferromagnetic interaction that really dominates it. So it is a very good example of the spin-a-half tagging the antiferromagnet. So in three dimensions, the tetrahedron is to 3 dimensions, what the triangle is to 2 dimensions. Okay? And we can also form networks of corner-sharing tetrahedra and edge-sharing tetrahedra, the same way we can form corner-sharing triangles and edge-sharing triangles. So if you make up a network of corner-sharing tetrahedra, you get this cubic network that you can see over here, which is known as the pyrochlore lattice. And the pyrochlore lattice, also lends itself very strongly to geometrical frustration. And this is a particular manifestation of it, which I'm going to describe to you now. It's going to sound kind of contrived, but it's actually very common in nature. And so this is our fundamental building block. It's a tetrahedron, and I'm going to decorate it with 4 classical spins. So again, the dipole magnetic moments, I'm going to think of them as little arrows. And the part that's going to sound contrived is I'm going to say that each of these 4 sites has its own easy axis, so it has its own direction that it wants to point along. And then I'm going to couple them not antiferromagnetically, but ferromagnetic. But the ferromagnetic coupling in the presence of these non-collinear easy axes, means that it can't form a fully ferromagnetic system. So you can see, just by this diagram here, that there is a net magnetization to this one tetrahedron, right? It's pointing from your left to your right in here. Okay. But the magnetization is not 4 times the magnetization of one of the spins, it's less than that. Okay. And in fact, you could work out for yourself that there's 6 equivalent ways of doing this. Okay. So you can minimize the energy, the exchange energy, and the easy axis energy by having 2 spins point in and 2 spins point out on each of the tetrahedra. Okay, and there are 6 ways of doing that for each tetrahedron. So there's a degeneracy of 6 connected with each tetrahedron, and then we're going to connect the tetrahedron together to fill 3-dimensional states. And as you do that, you'll generate, again, what's referred to as extensive degeneracy. It's a degeneracy that grows very fast with system size, and that degeneracy leads to what's referred to as a residual entropy, which is enough to preclude the formation of an ordered state at low temperatures. Okay. So this is referred to as the spin ice problem. Okay, and this here is the discovery paper in 1997, and it's called spin ice. And spin ice, I think, in my lifetime, this is one of the great branding successes in physics. That people like to say spin ice, even people that don't know anything about the problem, they like to say it. It's appeared on the Big Bang Theory and all that thing. So it's really a great success, and it actually means something. Okay, and it's something that it means is that the statistical mechanics of this problem of having two spins in, two spins out, actually it's the same problem as the statistical mechanics of proton disorder in solid ice. So the solid ice that flows around your drain, and that is out on the sidewalks right now. Definitely can. There's a little bit left here. But at any rate, most chemists and some physicists, know that ice is actually not an ordered solid. Although if you've fallen on it, there's something about it that's ordered. And so what is ordered, of course, is the oxygen. But the protons, the hydrogens, are not ordered, and the reason they're not ordered is because once you ionize hydrogen, you're left with a proton which has no size, right, on the scale of atoms and such. And so the protons can sit right on top of the oxygens. And the net result is that you get the same degeneracy. You end up with two protons sitting close to an oxygen and two protons sitting farther away. And there's only local constraints on the order. There's no global constraints on the order. Anyway, that's what it's called spinings. So this sort of problem has been enormously popular. And as I was mentioning, there, just like was the case with the triangles, with the tetrahedra, we can connect them together to fill three-dimensional states in different ways. So this is the way that I just talked about previously, which is a network of corner-sharing tetrahedra. We can also make a network of edge-sharing tetrahedra. Okay, if you make a network of edge-sharing tetrahedra, you get an FCC lattice. Okay, that's also a very common lattice in nature, so it doesn't have to be studied within this class of compounds, but there's a class of compounds known as the double perovskites. I'm getting a ringing noise. I'm not sure what that is, but anyway, we can just ignore it if you like.
It's green energy calling.
Right. So this is the crystal structure for the double perovskites. There are thousands of double perovskites that are known, this is actually the structure of perovskites. And Raphael's talk, he also talked about perovskites. And so perovskites are this assembly of corner-sharing transition metal 06 octahedron that you can see here. And these have the chemical composition AbO3, but they're, as I said, they're made up of a transition metal in the middle of this 06 octahedron, and then the octahedra are joined at a single vertex. So to go from perovskites to double perovskites, basically what you do is you alternate the transition metal ion that's in the middle of near neighbor 06 octahedron, so that you end up with these blue and these orange transition metal 06 octahedron, and then the chemical composition is A2, B prime, so these are the two transition metals 06. And this structure actually has great flexibility. There's really enormous amount of things that you can do with it. And just to give you an example, this is a family of osmium-based double perovskites that we've studied. And because we can control the oxidation state of the B site, so you can have, say, sodium, which is 1+, zinc, which is 2+, this magnesium, which is 2+, yttrium, which is 3+, and so forth. By controlling the oxidation state of the B site and also of the A site, you can have osmium in 3 different oxidation states. 7+, 6+, and 5+, and that corresponds to a single 5d electron, 2 5d electrons, or 3 5d electrons. So it really gives you a lot of variability. And I should say that because there's so many of these double perovskites, our group has focused on that small subset of double perovskites which stay cubic. So they stay in this sort of structure. And so the magnetic sublattice ends up looking like this, FCC, which makes it maximally frustrated. Most double perovskites actually will not stay in this structure, and they'll distort, and it's easy for them to distort because they just have to tilt their octahedra. So this is what actually most of them end up looking like here. But this is the other class of materials. Okay. So going back to the parafluors, there's also very many of these. So they're made up of materials that have a chemical composition A2B2O7, where the A site is typically a rare earth site that's trivalent. The B site is typically a transition metal ion that's tetravalent. Okay, so the example that I'm showing you here is cerium-2, zirconium-2, oxygen-7, and cerium in its 3+ oxidation state has a single 4f electron that's present. And if you go through Hund's rules, you come up with J = 5/2 for the total angular momentum degree of freedom. But with this class of materials, actually both the A site, which is shown in blue here, and the B site, which is shown in red, they both independently form networks of corner sharing tetrahedra, which are interleaved with each other. So again, we have tended to study the ones where there are only filled orbitals associated with the red tetrahedra, so that those are kind of magnetic vegetables, whereas there are partially filled orbitals associated with the rare earth ones. And it's not quite true, but it's almost true that you can, for a given B site, you can start at the beginning of the rare earth series and just go all the way across, and generate different parafluors with different number of 4f electrons, and that will give you, different size moments and different anisotrophies, and that will generate a whole host of different ground states, some of which are more interesting than others. But the one that we've been focusing on is the ones that are shown here, which are potential candidates for quantum spinites. So quantum spinites is the quantum version, not surprisingly, of spinites, and it has a whole host of interesting properties that I won't be going into here. And basically anything that you can look at here has some interesting phenomenology associated with it. So one thing that is kind of interesting and makes life relatively easy in the study of these rare earth-based magnetic insulators is that the energy scales that are associated with the magnetism actually separate out nicely. And so the highest energy scale, because we're down near the bottom of the periodic table, tends to be spin orbit coupling. Okay, so the spin orbit coupling, as you probably know, was as was discussed earlier, it's what connects the lattice to the spins. But actually, its origin is, at least in insulators, is that the magnetic electrons with their spin, are orbiting around some positively charged nucleus. But in the rest frame of the electron sees the positively charged nucleus orbiting around the electron, and it sees this circular motion, or almost circular motion, of a charged particle, which is then going to generate a magnetic field in the rest frame of the electron, and that magnetic field can be coupled to the spin. And at the bottom of the periodic table, that's actually quite a strong effect. And so the spin orbit coupling is on the order of hundreds of milli-electron volts in these rare earth-based insulators. So that J = 5/2 that you would have with the 4f1 Hund's rule ground state, it's separated by about 250 MeV to the next spin orbit multiplet, which is J = 7/2. Okay. And then the next highest energy scale is the crystal field effect. So these are, the effect that the rare earth ion is not, is safe, it's not in a vacuum. It's got these oxygen 2- ions immediately around it. So it's in this very strong electronegative environment. And that will split, so that means it sees a very strong electric field gradient And that will split these 2J plus 1 full levels. So that's 6, there's 6 levels here that will split up because of the crystal field effect. And in this particular system, it gives you these 3 doublets. So that's on the energy scale of about 10 MeV. And then finally, the energy scale that most physicists are interested in is the inter-ion exchange interaction, because this is what gives you phase transitions. And this is the J that we were talking about before. But the J that we're talking about here for the rare earths is at a very low energy scale. Of order 10 Kelvin or less. But nonetheless, this is what gives you spin waves and phase transitions. But everything here basically sets up, the nature of the magnetic moment that you have to deal with, and its anisotropy. That's all determined by by these crystal field effects, following on from the spin orbit coupling. And and so as I was mentioning, in these real root pyrochlores, you can almost go across the rare earth series, and each one of these will give you a different type of, different size of ordered moment, a different size of moment, but it'll give you a different type of anisotropy, either Ising-like, XY-like, or Heisenberg-like, different interactions, and then different ground states. Okay? And as I said, the ones that we've been trying to follow up on are the ones that have these quantum disordered ground states. And so, as a last example of this, when I talk about networks of triangles, it seems natural because the triangle itself, lies in a plane. It is to put together your networks of triangles, into planes, and you get these, these different two-dimensional lattices. Well, you don't have to do that. You can have neighboring triangles, at least if they're corner sharing, that actually are non-coplanar with respect to each other, and that happens also often in nature. And there's a whole bunch of these materials which we refer to as garnets. So wherein there's a magnetic species like gadolinium, erbium, or dysprosium that lie on what's referred to as a hyperkagame lattice, and it's a Kagame lattice in the sense that it's a network of corner sharing triangles. But the corner sharing triangles are non-coplanar and they span 3-dimensional states as well. So that's another family of highly frustrated magnets. And actually, interestingly, when we were trying to study this particular, 2-dimensional triangular lattice system, erbium, magnesium, gallium oxide, we actually discovered that if you mix the appropriate elements here in proportion, that should give you this composition. What is actually much more stable is this structure here. So some of these structures can compete against each other when you're doing the material synthesis. And so what we discovered was that this is actually very easy to grow, and this is actually very hard to grow as a single-phase material, right? And actually, so if you're trying to grow this and you grow this, you also get, see, this doesn't have any magnesium, so you end up with some magnesium oxide left over, and that's a clue that they're competing against each other. Okay. I think in the interest of time, I'm just going to skip over this. I was also going to talk about highly spin liquid candidate ground states that do not require geometrical frustration. And in these cases, this is also very interesting. In these cases, they actually require some bond-dependent anisotropic exchange terms. And there's a subset of these that are known as Kitaev interactions, which are very topical. But I think I'm going to try to skip and finish with just a couple of materials related examples. But this is kind of an interesting slide. Actually, it refers to this ruthenium trichloride, which is this potential Kitaev ground state magnet. But this material was proposed as a Kitaev ground state magnet in about 2012 or so. And this just shows you the evolution of the size of single crystals that could be produced as a function of time. with a very large amount of both manpower and money going into the effort to produce it. So, this is not a typical crystal growth, project. This is the best case where people desperately want to grow this as a large single crystal. And, you can see that there is progression on the scale of a year, but to go from 20 milligram single crystals to 3 gram single crystals is what a 5-year project. I wouldn't even guess at how much it ended up costing. So this is not necessarily all that easy. And these materials, even when you grow them, relatively simple measurements like heat capacity can show you that there's a lot of sample variability. Okay, so there are aspects of the materials prep and crystal growth project that are uncontrolled. Okay, and you end up getting what you get. And actually, here's another example. This is another example that I'm very familiar with myself. This is in 2 classes of pyrochlore magnets. And this particular figure, so I spent about 10 years studying this material, but this particular figure is not from our work. It's from some work out of Tyrone Queen's group at Johns Hopkins. And it shows you how much the low temperature phase transition in this material can vary by just changing the stoichiometry of the crystal at about the 1% level, right? So you get a variation of this particular phase transition by almost a factor, well, definitely a factor of 2 by 1% variation in the stoichiometry. And there are other examples. So these are 2 pyrochlore antiferromagnets. For whatever reason, this material here, no matter how people grow it, they always get exactly the same phase transition. It's always at this 1.3 Kelvin. And actually, to get this phase transition to move, you have to disorder it by almost 50%, right? You can disorder it by 50% or close to 50%, and you still get a well-defined phase transition. So some of these systems are extremely sensitive to disorder, in this case in the form of non-stoichiometry, and some of them aren't. And the precise reason for that actually is not necessarily clear. And this is the final example, which just again shows that you can either generate a phase transition or not on the basis of non-stoichiometry that's at a level that's very hard to measure, okay, and that people don't even actually think of when they're making their materials. They don't, you might think, well, I made a weighing error and about 5% more, 5% less. You never think that you've got, 0.5%, you're 0.5% out of that sort of thing. Anyway, this just showing you some of the pitfalls associated with this. And these are my overall conclusions. So there are now many platforms to look for exotic ground states that are generated by HFM. In most cases, the geometrical frustration or the interesting novel state is predicated on geometrical frustration, and that involves networks of triangles and tetrahedra. Not exclusively, you can also have these bond-dependent interactions, but that's a very common way to go. And that in any of these studies, the material synthesis and crystal growth is really the pillar of the study. That if you don't get that right at the beginning, you're going to be fighting against it for full project. And my group, we grow our own materials mostly, not exclusively. We grow our own materials, and then we carry out advanced characterization that ends up with neutron scattering studies. But everything depends on the materials prep at the beginning. And if you haven't done a crystal growth project or a materials prep project, actually, how many people here have grown any material themselves? Well, it's pretty good. Okay. Well, so maybe I'm preaching to the choir here. But I would say that a successful growth takes a lot longer and a lot more effort than most people appreciate. And it's not a single event, as you probably realize. It's not that you grow the material, you celebrate, and then you take it off from the neutron beam or whatever, and do your experiments and write it up and wherever. Right? It's you grow your material, and then you've got this huge back and forth between different types of characterization, definitely X-ray scattering, probably switch susceptibility, maybe heat capacity, and so on. This goes on and on, right? And to make sure that the atoms that you wanted in your crystal are actually in your crystal, and so forth. So there's a lot of back and forth. And at the end of the day, disorder is present in all materials, and almost everybody understates its importance. Okay? And actually for materials with highly frustrated ground states, so spin liquid ground states, quantum spin liquid ground states, a surprising fraction of them show this extreme sensitivity to disorder, which is difficult to control and difficult to even characterize. So it shows up as sample variability. And the reasons for this are not very well understood. And I think I'll finish off with a slide that I usually don't show in public, but I do show it to my students. And it just shows the time evolution of how much we love our crystal. And of course, we start off, completely in love with our crystals, right? And other people, and they have their problems that we don't. And anyway, it oscillates as a function of time. And in the end, we get very, circumspect about it and philosophical. We've done what we've done. Okay, well, thanks very much. Sorry for me.
Where are you on this?
Well, wherever.
So it averages to basically.
Yeah.
All right, time for questions.
I have a question about the IUCL3, like also the timeline of the crystal growth inside there. I was wondering, because there was an interest in growing large, so what was the interest, or was it like, is there any applications that where now was evolving?
Yeah, so it wasn't for application reasons. I mean, so larger single crystals will allow you to do, the full suite of the advanced characterization. So some, as you probably know, some types of characterization, it almost doesn't matter how small the crystals are. If you can see them, they're probably fine. For neutron scattering, so anything that's a volume growth, and neutron scattering, to the extent that the materials are not absorbing, or the nuclei that we're studying are not absorbing. If it's not absorbing, it's probably a volume growth. So if you put twice as much volume in your crystal, in the neutron beam, you'll get double the signal to noise. If you put 10 times as much in, you'll get 10 times the signal to noise. So you can so you can definitely work with crystals sort of this size. I hesitate to try to work with crystals this size, but here people Gaulin samples that are this sort of size, and I'm certainly glad that I don't have to do this anymore, but other people do. And so if that's what you want to work with, that is what we'll do. But you would prefer to be in this regime here. So that's the main reason why this effort to grow large single crystals. And of course, this is a big advantage for some techniques if they're not volume sensitive. So the techniques that are volume sensitive are definitely neutron scattering, definitely NeoStar. Those are the two that come to mind. Synchrotron X-ray scattering. The beam is the diameter of a human hair, right? So it's not.
So one of the training modules involves co-aligning crystals.
Great. Yeah.
So we're trying to teach good crystal growth
right
tactics here, and that's one of the reasons we're doing it.
Yeah, and it builds character.
Yeah. There was a question.
Right. So this is specific to honestly liquids and basically things that shouldn't be on phase. They should. So you're going through and you have some variation in your crystals, And you often have to do low temperature characterization, which is expensive and time consuming.
Yeah.
How do you get yourself from declaring victory when you don't see a phase transition a couple times?
Yeah, so the great thing about our line of work is that you don't have to police yourself. You're going to be policed. Right? There's a whole community out there. So it depends on the exact area. But like study of the power floors. So I published my first paper on power floors in 1992. And at that time, the only existing literature on power floors had nothing to do with magnetism, it had to do with ionic conductivity. Nobody in physics was interested. So, you know, so there was a period where I was working, roughly speaking, by myself. But now, you know, if I have a power floor project, you know, as I do with Jonathan, you know, I know with certainty that there's maybe 500 groups that are working on it, or you know, it could be as small as 2, and it could be as large as 5. So if you're working in a topical area, what motivates you to get things right is if you don't get things right, someone else will find out, and you know, it's not the end of the world, but I'd rather find out myself. And so our community keeps us on. And you know, that's the way it works. And of course, yeah, well, as everyone here knows, you know, all things being equal, I'd rather publish sooner rather than later. Right? And I'd rather publish more rather than less. But you know, you've got to get it right. And anyway, so it's you know, the community, the community really is important, and they really will keep you on. And you know, so some of these projects have now evolved over a decade and such, and so you know, the techniques themselves evolve. Like neutron scattering measurement now, you know, might have figures of merit that are a factor of you know, 10 to 50 times, you know, better than they were 25 years ago. And crystal growth techniques have gotten better. You know, image furnaces, you know, it's a practical thing on image furnaces. They're when I got my first image furnace, there was only one type of image furnace, you know, now there's about 5. And you know, so things evolve, things get better.
Questions? I know you're hungry to ask questions. No, okay, so we're gonna wait here until we. All right, thank you, Bruce. Okay, so we have lunch now, we should have lunch ready. And we start again at 1 o'clock.
Thank you. Good. I'm gonna turn this on.